Okay, everybody, welcome to today's lesson. We're going to be talking about definite integrals, which we've already had an introduction to, and we're going to take a look at some of their properties and antiderivatives, and we're also going to look at a couple new rules and calculations of what we can do with antiderivatives and integrals. You need your notebook and your calculator. If you also have your latest foldable, we're going to be adding a couple things to that. If you need a new one, you can obviously make one with a piece of paper at home or wait until the next day that we're in class here. So as always, make sure that you pause and rewind if something doesn't make sense. And if you're coming into school then the next day, make sure that you're asking questions about what we're learning here. All right, let's go. So we started looking at integrals, and now we need to take a look at a couple properties of these. I don't think these need to go in our foldables because they're going to become pretty self-explanatory after a while, and we won't look at them as rules. But I would put these into your notebooks as properties that we can take a look at here. Okay, so the first one, we can see that I'm integrating from a to b of the integral of f of x, and again, that would find the area underneath the f of x curve from a to b. And we would take the antiderivative and evaluate it, the antiderivative at b minus the antiderivative at a. Remember, there's a subtraction that happens when we're evaluating a definite integral. Well, if I switch the order, and now it's b up to a, well, that would mean that the order of my subtraction has been changed. So therefore, I'm now going to have the opposite of what I would have. So if you switch the order and the upper and the lower limits of integration from instead of a to b to a, then you're going to get the opposite answer. So that's this first property. Reversing the limits changes the sign. All right, the second one hopefully makes sense either from a graphical aspect or the actual antiderivative calculation. If I integrate from a to a, well, think about it on the graph. If I'm going to find the area from a to a, how much area is underneath of there? Well, there's none, because it would just be some little thin strip. Also, if I take the antiderivative, it would be the antiderivative at a minus the antiderivative at a, and obviously that's going to be equal to 0. So that one's pretty straightforward. This next one is what happens if you have a constant. Now remember, we're going to take the antiderivative of our functions, but if I have a constant, just like differentiation, I need to ignore the constant, so that constant can come out in front, and that's what this new property is talking about. There isn't a product rule for antidifferentiation, but obviously antidifferentiation is going backwards from differentiation, so we don't really need to affect that constant, just like in there. With our product rule, half of the product rule would have disappeared and went to 0. So this will be helpful to get kind of constants out of the way so I can just focus on the function itself to anti-differentiate that one. Again, make sure you pause if I'm going too fast. I got 2 more to go. Okay, this next one here, number 4, is if I'm adding 2 functions together on the same interval from a to b, well, I can split that apart as the integral from a to b of f of x plus the integral from a to b of g of x. I can actually evaluate. Now, this only works because they're on the same interval for those integrals. And this obviously would work as well for subtraction. It doesn't work for multiplication and division because what we're really doing is we're adding or subtracting areas from each other. So I can add an area to another area, or I could subtract an area from another area. I can't multiply areas or divide areas. I mean, even from a unit perspective, I can take centimeters squared plus centimeters squared. That's still going to give me centimeters squared, and the same thing for subtraction. But if I take centimeters squared times centimeters squared, well, that's going to be centimeters to the 4th, and no longer does that represent an area. So this only works for addition or subtraction. All right, and number 5, this last one. This one we might be using more than many here when we're working. So I've got an integral from a to b of f of x, and then an integral from b to c of the same function f of x. So if you look at my picture down below, my integral from a to b, this first integral would find that area. And then my integral from b to c would then find this area. So therefore, I can add those 2 areas together, but then it would be the integral all the way from a to c. And that's what this last integrals are saying. they can be added and or subtracted. I could subtract them as well, but in this case I'm doing it as an addition. So A to B, and then wherever B picked up from, then the next one's going to go from B to C. And then so in the end, I would then have an integral from A all the way to C. So that's a pretty common integral property we'll use, especially when we're dealing with areas under the curve. All right. So going to do a couple practice problems here. Let's just first refresh. So what I'd like to do is evaluate these antiderivatives, or these integrals, I should say. So I've got a constant function of 0.5. So the question is, what's the antiderivative? What function has a derivative of 0.5 or a half? Well, that's going to be 1/2 s. Now, how did I know it was s? Well, because of the variable of integration right there. So derivative of 0.5 s is just going to be 0.5, so that looks good. So I bring my lower limit and my upper limit over with this vertical bar. And then always the upper limit goes in first. So 3.4 goes in first, minus 0.5 minus 2.1 goes in second. I'm not going to evaluate this. This is just now. So I'm putting in this in first, this in second, and it's always subtraction. Now, in the end, it's going to turn into be an addition because of the subtracting a negative number, but ultimately, that would be my value. So what do we really just do here? It's a constant function up at 0.5, and I'm going from negative 2.1 to 3.4. So I'm basically finding the area of this big rectangle. And it kind of makes sense in what I'm seeing here. So the whole width of the rectangle would be 3.4 plus 2.1, and that's happening in this calculation. And then just multiplying by a height of a half. So it's just really finding the area of a rectangle. Same thing with this next one. Antiderivative of square root of 2 dr. Well, square root of 2 r. Again, that's another reason why we have this variable of integration, so I know what the variable was. And then substituting them. And so I get in the end square root of 36 minus the square root of 4. Oh, this I can do. So apparently the area underneath of this square root function, this constant function up at the square root of 2, from root 2 to root 18, that area inside of there is exactly 4 squared units. So again, that's how we evaluate definite integrals. So let's properties. All right, so now I'm not going to be given a function here, but I'm going to be given some information. So I know that the integral, and this is off of my screen. Give me a second here. All right. The integral from 1 to 9 of f of x is negative 1. The integral from 7 to 9 of f of x is 5. And the integral from 7 to 9 of h of x is 4. So I don't know what these functions are, but I know what their definite integral values are on certain intervals. So let's, all right, letter A. So letter A, negative 2 f of x, and I'm integrating that from 1 to 9. Well, this is the property that says I can factor out the negative 2. So, and then I go up and take a look. What is the integral from 1 to 9 of f of x? Well, that's negative 1. And so negative 2 times negative 1 obviously gives me an answer of 2. And that's it. That's all we're doing. Let's try another one. B, I want the integral from 7 to 9 of f of x plus h of x. Well, that's the one where we're adding them together on the same interval. So that says that I can separate them. So f of x dx plus the integral from 7 to 9 of h of x dx. And then I just go to my information up above. So integral from 7 to 9 of f of x is 5. 7 to 9 of h of x is 4. So I get a final answer of 9. How hard is this? Pretty easy. Let's keep going. C. All right, now what's going on in C? Well, it's got a couple things going on. I got subtraction on the same interval, so I could separate them, and I've got some coefficients. So let's kind of do two things at once. So I can take that 2 out, 7 to 9 of f of x. And hey, if you know what you're doing, pause me. Go ahead and try it on your own. You don't have to wait for me. So I separated the integral and then factored out. So in the end, looks like I'm getting 2 times, now what's 7 to 9 of f? That's 5 minus 3 times 1. Oops, that's a 7. I can't even read my writing. 7 to 9 of h of x, that's 4. So it looks like I get negative 2 as my answer. And yeah, in the background, it's calculating areas under curves and all that kind of stuff, but we're just evaluating these definite integrals. We're not even thinking them about areas necessarily. All right, what's the integral from 9 to 1 of f of x? Well, if I look up above, oh, I only have 1 to 9. So if I switch 9 to 1, 1 to 9, I've now switched the order of the subtraction that would happen, just like in the last problems that I did on the other page, slide. So I have to make it a negative because I'm switching the order of subtraction. It's going to be the opposite of what I should get. And then so now, obviously, 1 to 9 of f of x is negative 1. So I get 1. Now, this one's a tricky one. I'm going to clear my screen here. All right, so now what do we got here? I get the integral from 1 to 7 of f of x. Well, I don't have that up there. So let's think about what's going on here. I know that the integral from 1 to 7 of f of x plus the integral from 7 to 9, picking up where the last one left off, of f of x, oops, dx, that's going to be equal to what? Well, I went from 1 to 7, then 7 to 9. That's going to be equal to the integral from 1 all the way to 9. So there we go. So what is the integral from 1 to 7 of f of x dx? It's going to be the integral from 1 to 9 of f of x dx minus, because I'm going to subtract this over, the integral from 7 to 9 of f of x dx. And then so now I can grab my values. Negative 1, 7 to 9 of f is 5, so I wind up getting negative 6. So we can look at these as kind of like algebraic equations. Each of these has a particular value, so I can set up the equation and then solve. I'm going to let you maybe try the last one on your own here. This one's a combination. It's a subtraction on the same interval, but I think the first thing you notice that you're going to have to do is you're going to have to flip these and then negate it, and then you should be able to solve each separately and then go from there. All right, going to try some of these then later tonight then. All right, let's keep going. All right. So let's review a couple things here. So the mean value theorem for derivatives, we have done this before, and it's probably on your foldable, but let's put it on there again. This is finding the average slope, where the slope of the tangent is equal to the slope of the secant, or in other words, I rock equals A rock. So the instantaneous slope, the slope of the tangent line, will equal the average slope on an interval as long as the function's continuous on the closed interval and differentiable on the open interval. So pause me here and then make sure you get this back onto your foldable. So again, we're going to see a mean value theorem for antiderivatives in a minute. Practice this real quick here. So mean value theorem, I'd like to find the value of c that satisfies the mean value theorem for this cubic function on the interval from 2 to 5. So my derivative of my function, my instantaneous rate of change, obviously is 3x squared. That's me doing this. And then on the right-hand side, I'm going to be finding the average slope. So f of b minus f of a all over b minus a. So 3x squared is going to be equal to, now I'm putting this in, so 125, that's going into the function, minus 8 over 3. I'll just do my calculator here quick. 125 minus 8 divided by 3. Looks like it's 39. 3x squared equals 39. Divided by 3 is 13. So x is plus or minus the square root of 13. Now, square root of 13 is within this interval. Yeah, it's 3.6-ish. So negative square root of 13 is not within this interval. So square root of 13 looks like it's going to be my c value. Now, one thing I didn't do was to see if the conditions are met. So let's just double check. Is this function x cubed continuous and differentiable on the interval from 2 to 5? Well, yeah, sure. I mean, we even know what this function looks like. It is definitely continuous and differentiable on that interval. So there we go. This is something we've been doing for a while now. Slides. This is an average rate of change. Okay, an average rate of change is the slope of the secant. It's an average slope over an interval. All right. Can the mean value theorem apply on this cubic function on 0 to 2? Yeah, it's another cubic function. We could go through and do the same thing as well. So you can go ahead and do that as practice. All right, it's going to be similar to what we just did, taking the instantaneous rate of change equaling the average rate of change and then solving. How about these next ones down below here? Does the mean value theorem apply for this function on this interval? Well, I'm going to say no, because at x equals 1, the function is not going to be continuous. Because you can see that denominator would go to 0, and that would be undefined. That's a vertical asymptote in that function. So no, we can't use the mean value theorem there. What about this next one? Negative 3 to 3. Yeah, the mean value theorem is not going to work, not because it's not continuous, but watch when I take its derivative. So 2/3 x to the negative 1/3. And if I rewrite that, so 2 over 3, and a negative exponent will come to the denominator, and 1/3 is a cube root. So what's the big problem value? What can I have here for the derivative? Well, yeah, x equals 0. And since that's in the derivative, this graph is not differentiable at 0, and 0 is within my interval. So no, the mean value theorem will not guarantee. Could it happen? Sure. But I'm not guaranteed that the slope of the tangent is equal to the slope of the secant from negative 3 to 3. So keep our eyes peeled about using and not using. The AP exam will check to see if you understand here. All right. Here's an interesting concept. This is called the average value. So we talked about average rates of change. Let me go back. Well, now I'm talking about an average value. And what the average value is, when I jot this down, is it is a constant value that gives the same area underneath of that rectangle as if the area of function was a constant. So if I've got a function, in this case it's going to be y equals 1/2 x squared. Y equals 1/2 x squared, and I'm on the interval from 0 to 3. It has a certain amount of area underneath of it, that yellow area that you're seeing in this graph. Well, I would like to know how tall to make a rectangle so it also has the same amount of area. Average value is sometimes called the average height. So, well, we have ways of finding the area underneath of this curve. It's through antiderivative, so let's find that first. So here's my setup of finding the exact area underneath of my function from 0 to 3. So antiderive 1/2 x squared becomes 1/6 x cubed, again from 0 to 3. Upper limit goes in first, lower limit goes in second, which is just going to be a big fat 0. So I get 4.5. The area inside of here is 4.5. Squared units exactly. So now I need to figure out how tall must a rectangle be in order to have that same area. But I already know I'm dealing with a width of 3 for my whole interval. So if I take 4.5 divided by 3, I get 1.5, this value that you saw over here. So the average value of this function, 1/2 x squared on the interval from 0 to 3, is 1.5. That's how tall the rectangle would have to be. And it's a pretty easy calculation. What did we just do? We calculated the area. And how do we calculate an area? Well, we calculated it with a definite integral. And then we divided it by its width. And how do we find its width? Well, it's just the difference of b minus a. So that's b minus a. And usually you can write it as an integral over b minus a, but a lot of times you'll see it was 1 over b minus a. And that is my average value calculation. So on your foldable, on the outside, average value, and then my calculation on the inside. Here, some point within my interval, the actual function value will equal the average value. And that would be this value of c right there. Okay. So the mean value theorem for definite integrals says that for a continuous function, at some point in the interval, the actual value will equal the average value. So if I go back, that is my mean value theorem for definite integrals. This goes on your foldable as well. So on the outside mean value theorem for definite integrals, we already have a mean value theorem for derivatives. So my condition is if the function's continuous, then at some point the value of the function will equal the average value. The average value. So take a moment and put that into your foldable. Okay, so let's do one here. So what we want to do is we want to, given this cubic function on the interval from -1 to 2, it's definitely continuous, so I can use this theorem. Easy cubic function, no denominator here. Find the average value on that interval. So let's do that first. So my average value is simply the width, 1 over 2 minus -1, so that's 3, it's a width of 3, on the integral from -1 to 2. The x cubed minus 2x plus 4. And I'm going to cheat a little bit here. So I get 1/3. Take a moment and let's do this calculation on our calculator. Let's do the integral just as a refresher. I'm going into Math 9, and I'm integrating it from -1 to 2 of my function x cubed minus 2x plus 4 dx, and I get 12.75. And then divided by 3 is 4 1/4. So that's my average value. That's the average height of the function. So now I want to know, find a c value such as the average value is equal to the function value. So what we just calculated is that this is 4.5. Oops, 4.25. And I want to know, when does the function attain that value? So I'm really just asking this question. And at this point, there's a couple different ways you could do this. You could actually now take your graphing calculator. This is something you have to be able to do. Graph both sides of these equations as separate functions, and then find the point of intersection. Why don't you go ahead and do it that way? Now, if you go ahead and do that, I just paused and did that, I can see that I'm hitting it a couple different times, but I'm only interested on the interval from -1 to 2. So I'm even going to go in and change my Windows settings, make my x min -1 and my x max 2. So I can only then see the places where I'm interested in. And on this interval, it happens twice. So I'm just doing a second calc, intersect. So I'm on the graph, and I'm getting a value, I'm getting 2 of them. So x equals -0.126 is one value. And then second calc, intersect. It's going to ask you first curve, second curve, and guess. So just get close to the point of intersection that you're interested in. And I get 1.473. Always take it out to 3 decimal places. That's the rule on the AP Calc exam. So in this case, it happened twice. 2 times when the average value equals the actual value of the function. Okay, so looking at the difference between some subtle questions, this question's now asking me for the average rate of change of this function on this interval. Well, again, average rate of change is f of b minus f of a all over b minus a. So it would be f of 2 minus f of -1 all over 2 minus -1. That's my average slope. So average rate of change. When you hear rate of change, think slope. And average rates of change are basically slopes of secant lines. Take a second and calculate that value. Okay, so I got a value of 1. So now let's do this one. Calculate an average value of this function on this interval. So this is average value, so 1 over b minus a, integral from a to b, 3x squared minus 2 dx. So that's 1/3, and then I'm going to grab my calculator here and do another math 9 quick. So -1 to 2. Sometimes we'll do it with our calculator. Sometimes we'll do it by hand. I'm just looking for a value here, and I get a value of 3, and that also turns out to be 1. Huh, that's interesting. Is it just coincidence that they both turned out to be 1? I don't think so. Look at these two functions. What's the relationship? This function's derivative is this. So if I find the average rate of change of a given function, it's the average slope, so I'd have some kind of a cubic function, and I'm finding the slope on that from here to here, that slope of the secant line, that is equal to the average value on the derivative graph. So the average value of the derivative is equal to the average rate of change of the original function. Huh, that's interesting. Look at that. Here's my average rate of change of a function. Now, if I'm now going to take the average value of the derivative of that function, I'm doing this. Taking the average value of the derivative function. Well, if I go to integrate, what happens when I integrate a derivative? Well, I get its antiderivative, which is the original function. And how do we evaluate the original function here? I put in the upper limit, and I put in the lower limit, and look at that. The average rate of change of f of x, that average slope, is the average value of the derivative. Which kind of makes sense. This is an average slope, and what does the derivative graph? Slopes. So then it becomes the average value or the average function value on the slope graph, which is what we call the derivative. So that's a pretty big connection between those two things. All right. Just as a quick little reminder, lastly here, to calculate an average acceleration, we would be taking a calculation of the slope of the velocity graph. So I'd be taking the slope of the velocity graph, so the difference of the velocities over time. But then another way of finding average acceleration is by using the acceleration graph, is finding the average value of the acceleration graph. And because we know that the antiderivative of acceleration is going to give me velocity, it would wind up giving me the exact same calculation. So again, two ways to calculate average acceleration. And I could do this same thing with average velocity, just work back a function to my position graph. But average acceleration, you can find it as the slope of the velocity graph or the average value of the acceleration graph. Huge there. And this is just yet another proof that if you're interested, you can take a look. All right, there's a lot to digest. So at this point, I'm going to ask you to take a look at some problems, I think on page 290, playing around with those, and we'll definitely be talking about this over the next couple days. All right.